Here's your video on lesson 86, which is about independence as related to probability. So the first thing we need to know is, what does independence mean? Independence is when the outcome of one trial of an experiment does not affect the probability of the next trial. So I'll give you some examples of that, just in case you're at this point and you're still having some issues with the understanding. Some examples might help. So independent trials, ones that don't affect each other. They don't affect future probabilities. Some of the things that are independent is like coin flips. No matter how many times I flip a coin or what results I get from flipping that coin, all of my future coin flips are still 50-50 chances. Another thing that is independent is dice rolling. If I roll dice and I get low numbers, it does not mean that my next roll of the dice is going to be low or high. The chances are exactly the same, regardless of what past outcomes were. Another thing that we do that is independent is choosing and replacing. Because I'm replacing, it means that I'm putting back into the basket or the bag whatever thing I've chosen, right? So if I have a bag, right, I'll use a bowl because it's easier to draw. If I have a bowl, and in that bowl I have a bunch of apples, which I'm very sloppily drawing as red dots. I've got 5 apples, and I've got 5 oranges. Now, if I'm taking something out of that bowl, and I'm not replacing it, let's say I'm eating it, right? That is not independent, because I've changed the scenario. What happens in the future is dependent on what's happened in the past. For instance, now I have 1 less orange to choose from. The probability of getting an orange is only 4 out of 9, whereas previously, a second ago, the chance was 5 out of 10. So if I want it to be independent, one thing to not affect the other, I can reach into that bowl and pick an orange out at random. And then once I go, oh, I have an orange, that's what I've selected, I note it, I write it down, I keep it as a mental note, and then I place it back in the bowl. And then I can mix it all up, and then I can choose another fruit, for instance. That would be an independent trial because it's always out of the same number, 10. Now, dependent. Dependence is, well, simply, it's not independent. The keywords that typically mean that we're dealing with the dependence means those keywords are without replacement. And what happens is the sample space tends to get smaller. That doesn't have to be the outcome, but very, very, very often the issue is that we have 1 less in the sample space. So, for instance, some dependent examples. Our past trials affect our future probabilities or odds. For instance, if I have a pocket full of dollar bills, so this is going to be my pocket, it's one of those jeans back pockets, and I have a bunch of bills in here. And I've got a $1 bill, and I've got a $5 bill, and I've got a $10 bill, and a 20, and a 50. Now I've got these dollar bills sitting in my pocket. If I reach in and I take that dollar out, and I grab the 1 for instance, The chance of getting that 1 was 1/5. Now, if that 1 is gone, the chance of me getting a 1 again is 0/5. So what I chose in the past affected my future outcome. Let's think about it like this as well. Even if I wasn't dealing with the 1, let's say I take that 1 out. Before I took that 1 out, before that 1 was removed, the chance of getting any of these was 1/5, 1/5, 1/5, 1/5, and 1/5. That's the chance of pulling out any individual one of those bills. Now, if I take that $1 bill out, I take it out, it's gone. After the 1 is removed, if it's not replaced, the probability of getting each one of these is all going to be 1/4. Except the 1, which is now 0. Now, if I had just replaced that 1, if I had put that 1 back in, right? Put that 1 back in, all the probabilities would still be the same as what they were before. So if I replace it, nothing changes. If I've replaced it and nothing changes, that would make it independent. But because I didn't replace it, the 1 is gone, we have these after probabilities that are different. And when our probabilities after the fact are different, that's because they are dependent, right? One affects the other. So let's do a couple examples from today's sheet, see if we can get you used to the idea. We just need one equation before we move forward, and that's to check for independence. If it's a word problem, you really need to just read and think and figure out, well, does one trial affect the probability of a future trial? Does the thing I'm taking out of the bag or the bowl or the basket get replaced or not? Is the number of options I have decreasing? Now here's the formula. If the probability of A times the probability of B equals the probability of A intersect B, or A and B, then A and B are independent. So if that equation holds true, then events A and B are independent. If A and B are said to be independent, the question tells you they're independent, then the probability of A and B, or A intersect B, is equal to the probability of A times the probability of B. So this rule works both ways. If you check the equation and it works, it means they're independent. If they say they're independent, it means that the equation should work. Now let's do a couple of examples here. Let's do just say 5 and 7. We're checking to see if these are independent. That's the example says, identify if A and B are independent. So let's see. If they were independent, then the probability of A times the probability of B should equal the probability of A intersect B. So let's see. I'm going to change this to a different color. There we go. Okay, so this is the probability of A intersect B. That's 3 out of 40. The probability of A and the probability of B are both 1/4. So 1/4 times 1/4 is equal to 3 over 40. 1/4 times 1/4 is actually 1/16. So is 1/16 equal to 3/40? And the answer is no, these are not equal. So these are therefore dependent. If they're not equal, it means it is dependent. Question 7. Probability of A times the probability of B should be equal to the probability of A intersect B. So this is 7 over 10 times 11 over 20 equals, or should equal, 77 over 200. When I multiply these, top times top is 77, bottom times bottom is 200, and these are actually equal. So that means that they are independent. Try a few in that section if you're feeling good about it, or if you're feeling rusty, I think that you should back up a second and rewatch that and then try a few. Let's move on to the next section. Identify whether the following are independent or dependent, then calculate the probability. So I'm going to move on to one on the back. Independent or dependent. Let me just erase all this. Okay, 13. When I do questions like the problems, what I like to do is I like to ask myself, what do I need in order to make this scenario come true, right? Like if I'm the person facilitating this scenario, if I'm the person who's pulling coins out of his pocket, what do I need to get? What needs to happen in this scenario? So we're going to start off with that question. What needs to happen? So let's read this. There are 5 nickels and 7 dimes in your pocket. You randomly pick a coin out of your pocket and place it on the counter. Then you randomly pick another coin. Both coins are nickels. So I'm taking it out of my pocket and I'm placing it on the counter. So it's not going back in my pocket. These are dependent because it's without replacement. That's the key that tells me that these are dependent. So if these are dependent because I'm not replacing them, just want to plug this tablet in before it dies. Okay, so they're dependent because I'm not replacing them. That helps me understand a whole lot about the scenario. So now the question that I need to ask myself still is what needs to happen? Well, both coins are nickels. So I need a nickel and then I need another nickel. That's what I need. That's what needs to happen. So the things that I need to find out is I need to find out what the probability of getting a nickel is the first time and the probability of getting a nickel the second. And then, keyword and, means we're multiplying. So the probability of getting a nickel the first time, there are 5 nickels and 7 dimes, which means we have 12 total. Five nickels out of 12 total coins. The and becomes multiplication, and I need to think about the scenario. I have 5 nickels in my pocket. Once I've picked one, okay, that 5-12 chance works, and I succeed in choosing a nickel from my pocket. I take that nickel out of my pocket, meaning there are no longer 5, there are 4 left. And how many total coins do I have left in my pocket now? I've already taken 1 coin out from the first, so I have 11 left. Multiply across the top, multiply across the bottom, and then you can simplify. 5 times 4 is 20 over 132, which I can actually simplify to 5 over 33 by dividing them both by 4. And that is the probability of getting both coins nickels. So when you're doing it without replacement, when you're taking things out and you're not replacing them, what happens is my sample space gets smaller. So we would count down 12, 11, etc. And you actually just need to think logically about what we have left on the top. I'm not going to say that there's a standard way to do any of these, because saying that there's a standard way takes out the responsibility of you to use some common sense. So let's do one or two more, but we're going to do them quickly. There are 7 nickels and 5 dimes in your pocket, so still 12 coins. You randomly pick a coin out of your pocket, then return it. So it's going back in. So the amount of coins in my pocket is not going down. Then I randomly pick another coin. The first coin is a nickel and the second coin is a dime. So remember, same question. What do I need? What needs to happen? Well, I need to get a nickel, and then I need to get a dime. So what's the probability of getting a nickel? There's 7 nickels out of 12 total. And then, so the and becomes multiplication, a dime. There are 5 dimes out of still 12 total because I didn't keep it out of my pocket. When I took the nickel out, I then put it right back into my pocket because it says, I keep erasing too much, it says right here that I return it. So it goes right back in my pocket and I still have 12 left in my pocket when I go in to grab the second coin. Now I can multiply these. This becomes 35 over 144. One more that's dependent, because this one, if you could tell from the sample space not decreasing, this is independent. Because I put it back into my pocket, every trial is out of 12 and the probability is always going to be the same. Question 15. Last one that I'll do with you. There are 9 shirts in your closet. Okay, so that's cool. You tell me how many. 4 of them are blue. I'm going to get fancy here. 4 of them are blue. And 5 of them are green. You randomly select one to wear on Monday and then a different one on Tuesday. Okay, so I can't wear the same shirt 2 days in a row. So imagine it like this. I'm wearing a shirt on Monday. I throw it in the hamper. I don't know what your hamper looks like. It's kind of what mine looks like. It's got a lid. Okay, so whatever shirt you wear on Monday, you throw it in the hamper after Monday, and you have one less shirt to wear when it comes around to Tuesday again. So this is going to be dependent. Okay, so what do I need? What needs to happen? I need to get a blue shirt on Monday, blue, and then I need a green shirt on Tuesday. So blue and then green. The probability of getting blue is 4 out of 9, and then means I'm multiplying. The probability of getting green is going to be 5 green out of 8 total. Remember that after I wore that shirt on Monday, it went in the hamper, which I actually just realized I erased. So there were 9 total to choose from, but now that blue shirt that you wore on Monday is dirty. So it's in the hamper. It's waiting for wash. So you went from 9 total to 8 total choices for the second day. So 4 times 5 is 20 over 9 times 8, which is 72. That can be simplified twice, I believe. Divided both by 2 is 10 over 36. Divided by 2 again, and you get 5 over 18. And that's the simplest answer for question number 15. Now take the knowledge that I have given you and complete the homework sheet, which was actually separate, but looks just like this. Okay, and good luck.